Hello students, in this video I will introduce the module 3 of the syllabus of automata theory and computability. Before we go into the details of module 3, just let us have a quick recap of the concepts learned till now. So we had initially begun in our module 1, we studied the different types of finite state machines, or you could tell finite state automata. So we had studied three types, that is a deterministic finite state machine, non-deterministic finite state machine, and a variation of non-deterministic finite state machine, that was epsilon NFS. Okay. And then we had also seen the conversions of these FSMs. Next, in module 2, we learned the concept of regular expressions. We learned the concept of regular languages. We also saw how we could check on the equivalence of the regular languages and the finite state machines. And finally, we had studied the properties of regular languages. So this was what we had done in our module 1 and module 2. So previously we had learned a computational model, that is a finite state machine, and we had seen the concept of regular language. So we know that the class of the language which is supported by a finite state machine is a regular language, and these regular languages can be described in the form of regular expressions. Now just let us consider a language. For example, just consider a language L is equal to a to the power n, b to the power n, where n is greater than equal to 0. Now, what does this language describe? This language tells us that we need to have equal number of A's and B's, right? So the strings in this language should have equal number of A's and B's. So when n equal to 0, we will be having one particular string. When n equal to 1, we get one string. N equal to 2, we get one string. So it starts from, the value of n starts from n greater than equal to 0. So what would be the minimum string which we can have in this language? The minimum string which we can have in this language is epsilon, because when n equal to 0, a to the power n, b to the power n will be epsilon. Next, when n is equal to 1, we can have string AB. Similarly, when we write n is equal to 2, we can have AA and BB. When n is equal to 3, we can have AAA, BBB, etc. And this goes on. Now, just try to describe this language by means of an FSM. This language has to be described by means of a FSM or regular expression. Is it possible? It's not possible. We had seen this example in a module 2. The language L is equal to a to the power n, b to the power n, where n is greater than equal to 0 is considered as not a regular language because it is not possible to construct it given some finite number of states, because when we are constructing the FSM, it is difficult for us to count an arbitrary number of A's and then compare the same to the count of the number of B's. Now let us tell that for the sake of curiosity, we try to construct a FSM. So since the minimum, the string pattern is a to the power n, b to the power n, we will start constructing our FSM like this. We have got the start state, and we call the start state as Q0, and then we have to see A's. So On seeing a A, it goes to another state Q1, and in Q1 state we see that we see a B, and we go to some state Q2, and we tell that this is our final state. So now we need to have the strings which start with A, and the string should end with B. Here I'm just considering the scenario where n is equal to 1. We are not going to consider n is equal to 0 for this example. So for this particular state machine, so we are going to consider strings from n is greater than or equal to 1. So suppose your string starts with B, so we put it into a trap state. We'll just put it into a trap state, and I'll call this state as Q3. Okay, and in case here since this is DFSM, we are constructing a DFSM. A and B for Q0 is checked. Now in Q1 state we have written for the input B, but we have not checked for input A, so we can remain in the state. We assume that we can remain in the same state Q1. And in Q2 state, since the string has to end with B, we can remain in the same state. But whereas for A, input A in Q2 state, we put it into the trap state. So here to some extent we can tell we have generated the strings, right, of the format somewhere as which take A's and then which follows B's. So if we see this particular finite state machine, the expression is A star, B star. It is A and then any number of A's, B followed by any number of B's. So this is the regular expression which we can have for this finite state machine. But according to our question, what is the number of A's and number of B's which we need to have? The number of A's should be equal to the number of B's. So in case we have, if we are having this particular regular expression, if we have 4 A's, we need to have 4 B's. But it is not possible to construct a language in this for this particular pattern by using regular language. So we tell that we cannot have a FSM for this particular language. So what we try to do is we try to scale up and consider a new type of language which is called as context-free language. So we scale up, we go into constructing a new type of language which is called as context-free language, or also written as CFL. Okay, and we have got a computational model which accepts the language, that is push-down automata. So we have got this language CFL will be constructed with the form of C context-free grammar, CFGs. So in our module 3 of the syllabus, we will be studying about this context-free grammars and push-down automata. Context-free grammar and push-down automata. This part. So in module 3, we'll be studying the two concepts which are involved with context-free languages, that is context-free grammars and the computational model which accepts the context-free grammars, or we could also tell context-free languages, that is push-down automata. In the first half of module 3, we learn about context-free grammars. That is, we learn what is a rewrite system, we learn the basic definition of a grammar, we learn to design and simplify grammars. After that, once we are thorough with designing and simplifying grammars, we try to prove if grammars are right or not, or which can be accepted or not. After that, we go into the concept of deriving grammars. Then there is also concept of parse trees, a tree-like structure. You write the grammar in the form of tree-like structures. After that, we check on the ambiguity concept, whether more than one derivation can be obtained, or is it possible to obtain grammars in more than one way. And then we've got our general forms, normal forms of grammar. In the second half of the module, we learn the computational model which accepts the context-free languages, that is push-down automata. So here also we have two types of PDAs, that is deterministic and non-deterministic PDAs. The textbook is your first textbook in syllabus, that is Elaine Rich, Automata, Computability and Complexity, where the concepts are taken from the chapter 11 and chapter 12 of the textbook. So at the end of the module, you'll be able to illustrate grammars and automata, the recognizers for different language classes, by relating it to different applications like compiler design, your XML syntaxes, etc. So in the first half, what we do is we define and design CFGs, that is context-free grammars, and we modify ambiguous grammars so that we can disambiguate it and write grammars for programming language construct. In the second half, we devise PDAs for given language, that is push-down automata for a given language, that is context-free languages, and we note the difference between a non-deterministic push-down automata and a deterministic push-down automata, and we design push-down automatas for given grammars.